So we're on to buffers. This is a very important topic in this class and one that pertains to the reactivity and properties of acidic and basic substances. Let's start by reviewing the idea of dissociation reactions. Alright, so as you may recall from the previous lecture series, when you add an acidic substance to water, the acidic substance reacts by giving away its proton, yielding its conjugate base, and the water that has to behave as a base accepts the proton and yields its own conjugate acid, hydronium. In this lecture, but more importantly in the lecture to come, the titration lecture, we'll see that when you start with an acidic substance, you could actually react it with a stronger base than water and create something known as a titration curve. Now, specifically, if the acid is a weak one, you're going to find out that the point right here, this inflection point, which is known as the equivalence point of the titration, ends up yielding pH values greater than 7. And we're going to get to the specifics of that. But the thing to remember and recall right here is that reacting an acid with water will generate the conjugate base and hydronium. Alright, so let's do an ice-stable example of how you go about calculating the equilibrium concentrations and ultimately the pH of a solution that contains an acid or a base. In this case, we're talking about hydrofluoric acid. So the initial concentration is 1 times 10 to the negative 3, the Ka value is 7.2 times 10 to the negative 4, and the balanced equation is acid reacting with water forming conjugate base and hydronium. So we prepare our ice table, we input the initial concentrations, we only have information for HF, we don't have any information for hydronium or fluoride, so we assume them to be 0 to begin with. Notice also that I'm not using water or introducing water into the table because it is a liquid. Now the changes in concentration for acid-base reactions are kind of convenient because generally stated we are looking at reactions between conjugate pairs. And so the balancing coefficients by default are going to be 1 to 1. So the changes are going to be minus x and plus x. Plus x for the things you're forming, minus x for the things that you're reacting away. So you end up finding out your equilibrium concentration upon adding the two rows together. Right now, here's where we use the Ka expression along with the equilibrium concentrations. We know that x times x on the product side ought to be divided by 1 times 10 to the negative 3 minus x to yield the Ka expression. So we have, in other words, x squared divided by 10 to the negative 3 minus x. And if we divide 10 to the negative 3 by 7.2 times 10 to the negative 4, we're going to obtain a value that is not greater than 400. It will be smaller. So we can't actually disregard the x. So instead we're going to cross multiply. So we multiply both sides by 10 to the negative 3 minus x. That will equal now x squared, and we bring everything to the same side so that we end up with x squared plus 7.2 times 10 to the negative 4x minus 7.2 times 10 to the negative 7. And in this process, yes, you may have guessed it, we're going to have to use the quadratic formula. So the coefficient in front of the x squared, which is 1 in this case, is a. The coefficient in front of x is b, and the coefficient without the x's, negative sign included, is the value of c. So we input that into the equation, negative b plus or minus square root of b squared minus 4ac all over 2a. And we basically go ahead and simplify this. So multiply 4 by, or negative 4 by negative 7.2 times 10 to the negative 7. And basically add that to 7.2 times 10 to the negative 4 squared to get the following value, 3.4 times 10 to the negative 6. Take the square root of that value and add it to the negative b value that you had before. Upon dividing that by 2, we're going to get a value for x. And going back to the table, notice that x is the value of the hydronium concentration, the fluoride concentration, and HF. So you can actually input those values to get the equilibrium concentrations. But one thing that's going to be of most importance when doing ice-stable problems for acidic substances and basic substances is to find out the pH of the substance. So hydronium concentration right here is 6.15 times 10 to the negative 4. Take the negative log of the hydronium concentration and you will find the pH. So in this case, we're talking about a pH of 3.21. Notice that the pH value is less than 7, as it should be because we're dealing with an acid, and acidic substances have a pH less than 7. Alright, so that's what we call the initial amount of that acid. It's basically, if you have a concentration for the acid dissolved in water, you're going to be able to use an ice table to figure out the initial amount, the initial pH of that specific solution. Alright, now let's take a look at bases. It's going to be a similar idea. The base reacting with water, this is the base dissociation equation. Base reacting with water is going to yield conjugate acid along with hydroxide. And when we do the titration curves, you're going to find out that the equivalence point of a weak base with water ultimately yields pH values that are less than 7. That's at the equivalence point. What we're going to find out though at the initial point is that when we have a base in water, the pH is going to be greater than 7. Alright, so here we have a base, a nitrogen base. This is pyridine, and that's reacting with water to yield pyridinium and hydroxide. We're being told that the initial concentration is 10 to the negative 3 molar, and the Kb, which is what's telling you that this is a base, the Kb of pyridine is 1.7 times 10 to the negative 9. So kind of like what we did before, the initial concentrations will be 10 to the negative 3 for the reactant, 0 for both of the products. The change in concentration will be minus x plus x plus x, and your change will be 10 to the negative 3 minus x, x, and x. Alright, so when we set up the equation for this, one thing to notice is that the initial concentration, 10 to the negative 3 divided by the value of k, 10 to the negative 9, is indeed going to be a lot greater than 400. So right here, the minus x can actually be neglected. So when we write concentration of products divided by the concentration of the reactant, that should be a 5 by the way, we're going to have the following situation. 1.7 times 10 to the negative 9, which is the value of the equilibrium constant, multiplied by, is equal to x squared divided by 10 to the negative 3. The minus x has been removed because it is negligible. So all you have to do now is cross multiply 10 to the negative 9 by 10 to the negative 3. You're going to end up with 1.7 times 10 to the negative 12. And when you take the square root of that value, you end up with the value of x. Now the value of x has to be placed back into the ice table. And in fact, this value is very small compared to the initial concentration. So that was a good approximation on our part. Yeah, this hasn't changed much, if at all. Now the value that we have here for x surmounts to the value of hydroxide. So what we can do is take the negative log of the hydroxide concentration to yield the pOH. So this value of 5.89, you got to be careful not to call that the pH. It is not the pH because the x value corresponds to hydroxide in a base dissociation equation. So what you need to do to get a pH is literally subtract it from 14. Subtract that pOH value from 14. And that will yield the value of your pH, 8.11. which in fact is greater than 7, implying that the solution is basic. Alright, so this is looking so far so good in terms of the reactions. What you do need to remember is how to write your Kb equation, how to write your Ka equation. And the moment you know that you're dealing with Ka, you have an acid reacting with water. The moment you know that you're dealing with Kb, you know that you're dealing with a base reacting with water. And in either equation, you just have to follow the rules of conjugate acid and conjugate base derivation to derive the products. Alright, so I'm going to stop the first video right here, and on the next one we'll start talking about buffers.